Welcome back. Welcome back on board. So we were trying to start the step 2. We just gave a look to the Discord. Perhaps some people has really taken his break. So I let you a few minutes to go on. Oh, I see I have a few questions there. I will answer there, and afterwards I will just start my poll just to check if some people has already finished the step 2 or not. But please take your time to try it. So I remind the aim there is to move from single task to parallel 4. One of the things to do for this is not to keep the loop on iteration in the task, but put it outside. And you replace the 2 loops on rows and columns by the call to parallel 4. So the pool. Oh yeah, I don't think ICPX is the name of the image there. It's Intel ICPX. If you want to check the name of the image, just go there to the GitLab repository. You can move to the project called Grayscott SYCL setup. And there on the left menu, you should check deploy container registry. And then you have the list of available images. So the base one, you don't care because they are used for the other one, but the main images interesting are Intel ICPX today to use a OneAPI Intel implementation of SYCL with CPU and the adaptive CPP if you want to try the adaptive CPP implementation of Heidelberg. Next week, we'll use GPU. You will need the image which end with CUDA, which have CUDA installed as a backend on top of. It's okay if you have an NVIDIA card, of course. If you have an AMD card or something else, you will have to make your own installation. So for the moment, I have 1 vote for parallel 4. Please, if you succeeded, also in the remote seats, please vote on the Discord so that we see that people is succeeding or not. The solution on the step 0?
Yeah, because
Okay.
so I
Let's show it.
yeah, because I'm a bit late. I had a problem with the installation.
No problem. I think we are on time largely, so
Okay.
you can ask questions also remotely about step 0, step 1, no problem.
Okay, so I tried to implement the std for each in Grayscott.cpp, and I have a problem with tbb.
Oh,
so well, it's
an
again
installation problem.
Yeah, again.
I dislike them very much.
Yeah.
So
it seems like tbb is not installed in my
you're compiling with ACPP or ICPX?
ICPX.
ACPX. Normally, that's what I tried on my side with the Docker image. So working, normally what happens is that if you take the script there, okay. Yes. Perhaps it's better if you say to him that you need a CPP. So what I suggest is you edit collier.bash, and there, instead of duplicating this line, semiclist src.txt, perhaps try with cbb.txt.
Okay.
This CMake file will add a find on TBB, etc., etc. I'm not sure because I would think it's not needed because normally ACPX is using TBB natively. So I'm surprised you like it, but try perhaps this. I will try on my machine just to check that the solution is working because as usual, I was doing some modification yesterday. So perhaps I've broken something.
Sorry, just you wrote TBB after point source. That's right.
TBB there.
Okay,
Yeah.
but do we have this file? I'm not sure.
Yeah, because all those files, they are taken in SYCL setup.
Yeah, but I'm looking at it and I can see.
You don't have it?
Yeah.
Would be surprising.
Yes.
I will look at mine, but I hope it is added in the repository. But there, not in Docker, in CMake, I have this SRC TBB there.
Okay, well, I don't have it in mine, in my installation.
Perhaps that's a change I made yesterday or the day before. So all people who has done the checkout of setup 1 week ago or in advance, please git pull.
Okay, I will run git pull to add that. Okay, thank you.
Please git pull because I've made some recent change, especially to have something compatible with adaptive CPP, which has been added very recently in this work. So perhaps yes, you need git pull. So back to step 2, I will comment a little the solution. So that's my usual iterate. And actually, you see that before my loop on the iteration was within the single task. But because I want to use parallel for to loop on a row and columns, I need to put the loop on iteration outside the call to the. So I will call this parallel for as many times as I need iteration. Now I'm not just doing a single one call to single task. I will call parallel for many times for each iteration I want to do. I have prepared those range because that's the solution. So with ND range, but there's a simpler one with just range. But there we have the solution with ND range. So there I'm doing a global loop, which is NB row X, which is the initial size plus 2. I say minus 2 because I must apply my pattern to the global size minus 2. And I tried there, actually what I tried to do is to take control of the subdivision of my global space. And I put there the biggest number I can, so to have the less multithreading I can, because we have seen that multithreading is not so good for CPU. That's the maximum numbers I was allowed to put. The problem is that all this has been designed with GPU in mind. And with GPU in mind, you don't want big blocks, you want rather small ones. And I don't exactly know why, but my implementation, Intel implementation, and adaptive also, they have a maximum size they allowed for the blocks. And if I put bigger numbers, actually I was trying to say I want as local NB row X minus 2 and NB colon minus 2 just to switch off the multithreading, but I'm not allowed to. So I have put there the biggest number allowed by the implementation. So to have the less threads I can, because I don't want too much threads. So that's why I put those numbers. If I think the multiplication of both, I was said the maximum number was something like 8,000. So there, instead of the explicit loops, C++ style for loops, I'm calling my parallel for on those sides. So I want the global, which is NB rows minus 2 and because minus 2, the local one, the biggest I can, and then my lambda function, my kernel. So there, because I'm using ND range, my lambda will receive an ND item. I can get the RNC this way. I'm asking for the global ID and of rank 0 and the global ID of rank 1. Actually, it's current row and current column. The rest of the code is not it's just the same. I'm not even sure why I have this indentation, which something which would need to be corrected. Okay. So just the code as usual, but instead of doing the loop myself, I'll just call parallel for. Where am I sweeping there? It's one element where I made, just for the game, a difference between what happens if I'm using adaptive CPP or what happens if I'm using Intel implementation. So if I'm using adaptive CPP, I would say that adaptive CPP is less flexible as what SYCL is asking. So after doing my iteration, I'm doing a wait and then doing the swap between my pointers. I must wait after each iteration before swapping, because my swap, as you see, my swap is not done in the queue. It's not something I'm doing in the device, so it's done on the host. So before swapping on the host, I must be sure that my parallel for is finished. So I need the queue wait. That would be the more canonical way to implement it. But if with Intel, he will do that. And with Intel, I remarked that I was able to submit to the queue the task of doing the swap. It's not completely allowed in a true SYCL, because normally when you submit something to the queue, it must contain one action, which is either a single task or parallel for, or something, or a copy of memory if you are using GPU, etc. And there, I'm doing nothing such of that sort. There's no action in what I submit to the queue. I'm not sure it's allowed, and I think it's why adaptive CPP say no. But Intel is okay. What's the benefit to do this with Intel is that I don't need to put the wait, because I will declare my queue. If I'm on Intel, I'll declare my queue as in order. And so I can send to my queue iterate, swap, iterate, swap, iterate, swap. And because the queue is in order, it will do one after the other. But you see this submission of something with no action on the device, just an action on the host. It's probably not completely in the spirit of SYCL. It's why adaptive CPP does not agree. And there I need to do the wait myself. So you see the same trick in the main. There, if I'm not on Intel, I'm doing a usual queue, and if I'm on Intel, I'm doing a queue which is in order, so to avoid the wait. That was just a game to show you that sometimes you may need to have some DS-defined, to have some subtle differences depending on the implementation you are using, which is bad, which is not what I would like. I would prefer single code run anywhere. But sometimes you may be needed to do this kind of tricks. So that macro is the way to know, am I using an Intel implementation or not? Apart from that, that's the usual code. I have the weight or not included in iterate. So before doing the extract, it's okay. I think I have the final weight. There, this one is needed, even if the queue is in order, because as I explained before, what I want to do after is extract, etc. It's on the host, so I must be, even with a queue in order, it will not wait if I don't ask for. So this one I need it. This one, it depends. I can avoid with the in order queue if I'm on Intel. So that's the basic parallel for. We see that we have the zero time, which is quite good, but a user time, which is huge, because as expected, we are doing parallel for, so it is doing multithreading. And as you saw, the user time is a lot more than when we were using the single task. This is the single task. asking behind the scene, asking 5 or 6 seconds, we move to 46. That's not a surprise. We have seen with the pure CPP code in the step 0 that for this problem, multithreading is not helping very much. So that's even worse. When we are working just with the for each and the STD par, I remember it was about 30 something, the total time. Now we are 40 something. And if I use the ND range as we have shown in the solution to make the bigger blocks we can, so to reduce the number of threads, it's improving a lot with Intel implementation. We move from 46 to 22 seconds. And it's a disaster with adaptive CPP. I don't know why. We move from 42 to 1 minute 13. So adaptive CPP has not loved at all or ND range. But it's worth to try several implementations, as I made in my postscript. Postscriptum 1. At a moment when implementing, I made an error. I revert. I'm back to you. I revert the row and the columns. You know, when you're talking about images, what is the first number? What is the second one? You mix them quite often. And when I made an error and revert my numbers, 120, etc., Intel has seen nothing. It was okay. But adaptive CPP noticed and said to me, oh, your subgroup is not a multiple of the global size. And thanks to adaptive CPP, I discovered my numbers were swapped. So good, always good to have several compilers and try both of them. And then I have a question or a comment.
A question. Does SYCL pinning the threads on the course, or it lets them move?
I'm afraid not, because I've read in some documentation. Sometimes I read it, but very, very little, the best I can. But I've read it somewhere that there are some tricks. If you know what is the backend, for example, if you know that's OMP, you can set an OMP global variables to pin the things.
Okay.
So probably this means that it's up to the backend and up to the implementation, but not at the SYCL level. And that's good or not, but I'm always sad that if you need to do some things to better drive the backend, it means that the SYCL level does not give you the way to do it yourself. But if you know the backend, there are ways to drive with global variables, OpenMP or OpenCL to say these kind of things. Second postscript, yeah, I already explained that trying in order just affect the queue, and so be aware that always when you have host code, you need the weight. Unless you use buffers on accessors. So the final step, perhaps we will finish before midday. The final step is to be back to buffers accessors. So the idea there is that we tried the parallel for CPU is not that good. So let's go back to the single task, which was better. But with all this weight that we can make errors with them, why not use the old style buffers on accessors on SYCL so that it will arrange for me the order of the task. So please try. In step 3, so the initial code is the code with the single task. And try to add in these buffers, wrap all your arrays in buffers, access the data through accessors, and see how it behaves, if it's better or not, as compared to the pure single task with pointers. Now we are trying single task with buffers. A key point there is that from the beginning, we were just using pointers. So we could call directly the single task on the queue. Now we need to build our accessors. So we'll need the 2 levels of lambda. First, we call the submit on the queue. Then we make the accessors. And then we call the single task on the handler. the two levels. Because if you don't do the two levels, there's no way to put the accessors, okay? So perhaps check, if you don't know how to handle this, check the slides from the beginning with the buffers, accessors examples, and reproduce it in the code. I see question about environment problems. Generally, if you use an Intel environment, with SYCL, you start by sourcing something like OPT, Intel, setvars, etc. In the images I'm providing, it's done by default. So normally you don't need to use them. But if you are on another platform, probably, perhaps, what you like is to source this environment file at the beginning so that you get access to ICPX. So about the question from Adrian, which has the error not finding the SYCL input file, header file. I'm not sure, it depends again on your platform. I guess if you have access to ICPX -F SYCL, I would think he will find the header file automatically. So
sorry, I had this error.
yeah.
To fix that, I have to run the CMake ICPX cycle.
Yeah.
Not just ICPX. And it was able to find a cycle doing that.
Yeah. Yeah, when you are doing Coliru, in this part of the practice, since we use SYCL, you should say Coliru, ICPX, not minus, tiret, SYCL.
Yeah, exactly.
But I think Adrian is trying to do it by hand, not with the CMake, probably.
Okay.
You know, he's giving us its compiling link. We can check what we have in the CMake, but I would think that ICPX has include directories hard-coded in it, but perhaps not. What do we have in the CMake? Let's check if we find a clue to help Adrian. But for this exercise, when I'm using from the setup, where is my setup is there, I'm using this CMake file. Perhaps I'm answering, perhaps you need to define the targets, but I don't see the link with the problem of include, not sure. But now the flags I'm using myself. -F SYCL, -F SYCL target, spears. When you are using adaptive CPP, you don't need to give the targets. By default, is managing to handle the situation most of the case, I think. I think that with ICPX Intel implementation, you must provide at least one target. I'm not sure, 100 sure. Another comment there, because since I'm there, I'm using those options with my ICPX compiler. It's because I've read the guide from Adaptive CPP that protest because they're often in the benchmark, ICPX is performing better. But often it's because they are doing tricky things with math. By default, ICPX is okay with fast math. And by default, adaptive CPP is not, like J++. So in a benchmark, when you are comparing the compiler and putting not so much option of compilation, sometimes Intel will win because he's tricky, I would say triché. He's cheating about the math operation using fast math where the other compilers are not. So in my comparison, in this practice, also in the project called Benchmark, where you have the whole code, I'm using those options to be sure that all the compilers are doing the same for what concerns the fast math possibilities, to be fair in the comparison. Okay, So back to comment on the final solution of the final step. So the main start as usual. Nothing new, basic image, extended image. Then the first new steps, I'm creating buffers. So as compared to my example at the very beginning, now I'm using range of dimension 2. That's one of the nice things with buffers is that it is an accessors. They are able to handle 2 dimension on your arrays. And you can give index with the 2 dimension. You don't have to compute yourself the index. So someday, perhaps with C++, we will have MD span with the possibility to have multi-dimensional arrays implemented in the standard C++, but it's in the norm, but not yet in the compilers. So it's nice for this to move to SYCL because at least we have the 2-dimensional arrays easily usable. So there I'm creating buffers, dimension 2, with the number of row plus 2 for the borders, the same for the columns. So I put a buffer on top of each on my arrays I want to work with. Remember that once you have done the buffer, never more access U1, V1 directly, or you have some kind of, how we say in C++, undefined behavior. So once you have the buffer, anything must be done through the buffers on accessors, not directly. Once the buffer is destroyed, if it is in a function, once it's deleted, you get control back directly on your arrays. But once you have done the buffer, only work with them. In my iteration, so I'm calling iterate, and iterate, instead of giving the arrays, I give them debuffers by reference. So let's see how it is looking like now. So iterate, receive reference to the buffers. My submit now, you see, has 2 levels. I will submit the first lambda, where I'm creating the accessor. So for each buffer I want to use, I'm defining the accessor, the input one read only, the other one write only. Then I can call on my handler, I can call CGH, it means command group handler. I will not comment more why it is called this way. So there I'm calling my single task, so what we call the kernel on GPU, even if the same concept. So this first lambda is catching things by reference so that the accessor is done on the right buffer, not on a copy. When I call the single task, this time I'm doing copies, but what I'm copying there and using is the accessor. So that's something copyable in the device, no problem. It's done, it's made to work this way. My single task, because I'm using a single task, not a parallel for, I'm doing the loop on the rows and column myself. But I don't need to compute some funny things to find the place. I can directly do there an ID, giving the current row I want to work with, the column, and this ID can be used between square brackets on the accessors. So I'm using my accessors as if they were usual arrays, and I can give them 2D indexes. Quite natural, nothing more to say. You see there with the pattern, also I'm doing 2D IDs. It's okay. One funny thing I can do after the submit, I can swap the buffers. I'm not sure I give the trick in the in the practice instructions, but I'm swapping the buffers. And so just after, I can again submit. And you see that the buffers have been swapped, but the new accessors, read-only, write-only, will be on the swapped buffers, and there's no problem. And will all of that written this way, the runtime of SYCL is able to know when he can swap, when he must wait, etc. You don't need anymore to worry about when to wait. even in the host code, what happened there is that when I want to access my buffers to compute my mean of V during the loop there, I will use what we call an host accessors. So that's a way to access the values in a buffer from the host point of view. And because, again, I use a host accessor, the runtime of SYCL will handle for me the weight which is eventually needed. And I don't need to worry about when to wait. Again, he will understand that he need iterate to be finished before I access to my, my buffer VB1. So that's the benefit of buffers and accessors. No need to worry about the weight. It is, and the price to pay is that, as far as I know, and I have read in the adaptive CPP guide, it's done runtime. So there's a small price to pay in the performance normally, because it's not, when you're doing the weight yourself, it's compiled. And it's already managing the binary, okay? If you do it with buffers accessors, part of it is done runtime. So it is taking a little time. But I think in this use case, perhaps it should not affect so much. But let's see what are the results on Cassidy. Oh yeah, bad clue there, swap on accessors. No, you can swap on buffers actually. There's an error. Okay. So what's the result on Cassidy for this? We see we have 3 seconds in ICPX, 6 on ICPP. So ICPP is quite stable for this. We always have our 6 seconds from the beginning. ICPX is not that good as if we have the sequential code, which were fast. We will go back on this after. And again, even if it's a single task, we have this mystery user time. It is doing thing in the background. I don't know what, but even a sys time of 32, I don't understand. But we'll work this week with the guides, the guy there to perhaps understand what's going on. It's a mystery. And so, as a sum up from what we get from the Intel compiler, so that was the time with the basic code, which stayed almost the best one. If I want to go fast, I can use for each an execution part without SYCL, or with SYCL, I can use a parallel for with ND range. I have almost the best time there, but it costs 20 seconds in the background. So if I want to do much job, perhaps that's not a good best. But if I have one job and I want it fast, I can use parallel for and the range. It will multi-thread, and I got the result very fast. You see that buffers, accessors, and but it's a single task, so no multi-threading there. But it's not as good as basic one, because with buffers, accessors, and single task, we are breaking the vectorization, the good vectorization of ICPX. So basically, moving to SYCL today, and with my level of knowledge, because I don't, perhaps there are a secret option in ICPX to have the vectorization in my kernels, but not found it yet. But for the moment, if I move to SYCL, which is a good thing when I will move to GPU later on, but I'm losing part of the vectorization today. I'm having this strange background multi-time behind, which I don't master. On the adaptive CPP front, quite something stable. Most of the time, we have these 60 or let's say 7 seconds of time, the same in real-time user time. With the for each, probably I lose perhaps some vectorization, perhaps some loop unrolling or something. It's a little less fast. When I'm multi-threading, I'm as fast as ICPX, but with parallel 4, I am this quite horrible global time. I don't know why. So if you see different things on your platform, I'm interested. Please share it with us in Discord, because I'm not sure. It depends on the machine you are using or your options, etc. So it's interesting to investigate if it's the same elsewhere. So as a conclusion, normally, especially when you prepare a move to be able also to run on GPU, and we will see next week that SYCL on GPU works fine. So you should use parallel 4, but we see that with parallel 4 on CPU, we pay the price that we lose the vectorization. Unless you are doing some tricky things with the backends, you lose the vectorization, and you have multi-threading that perhaps you would prefer not to have. But it's kind of price to pay. If you will move later on GPU, it should be fast. And that's my final conclusion. Thanks to you. Finished. If you have questions, and if you try later on with the work, please feel free to ask questions on Discord, on the SYCL channel. Try to answer all along the weeks until next Tuesday. Good lunch. A question?
It's not really a question, it's just a remark that I don't have this huge user and system time on
on your machine?
Yeah. So for example, for the third step, I have like 3 seconds for real computation and 1 second for user and system, while you have like 20 or 30 seconds. So
okay. Well, so if you have a little time, we'll try to investigate between Cassidy and your machine, what is the difference, and try to understand what's there is this difference. It will be interesting.
Okay.
Thanks for the comment. I will check. Une question sur le Discord. OK. Which channel? Question experts. OK. Do you think using subgroups? I don't. The subgroup has been designed with a GPU in mind. So in this practice, I tried to use them to reduce the multi-threading, which was not beneficial in our use case. But I think I'm not in the typical use. I think that currently, when running on CPU, all the compilers, they prefer to rely on the auto-vectorization. The problem is that as far as I can see, if I do a single task, a parallel 4 authorization does not work. So perhaps there are secret options in Intel compiler or adaptive CPP to get this auto-vectorization. Is still to be discovered. If you find one, I'm very interested to know about. But it's the same with, I would say that it's the same with usual C++ code. You see, they have done this for each transfer and the STD execution part. We have this STD execution unsec option, which is a way to ask in standard C++, please vectorize. And from what I observe, the compilers, they do not care. They are fighting for years, perhaps 10 years, 20 years, to have auto-vectorization working. So this STD execution unsec, they do not care about. If you don't ask it, they will try to auto-vectorize if they can. And if you ask for, they will not try more. So if you can try the step 0, if you try the for each with std, unsec, or nothing, in general, you see no difference because the compiler, what is Intel, J++, etc., they prefer to have their auto-vectorization working, and they don't care what you ask in your code. The only one where you see effect is std execution par when you ask for multithreading. This, you see the effect, but in general, unsec, I've never seen a compiler which make a difference if you put unsec or not. And I think using SYCL on CPU is just the same. They prefer the compiler implementers. They prefer to rely on auto-vectorization. The subgroups, it's mostly to be used with GPU. I tried to use it there to block the multithreading, but that's not the usual way to use it. I say other question. Has anyone tried inspected subgroup get local range today? I tried only on GPU, but I've not found a use with Grayscott use case. I have not found a way to use the local range and to access the local memory, etc. What SCMD width did you observe on CPU device? It is to be checked. As I said, I made some guess, especially when I see that ICPX is going a lot faster than others in pure C++ code. I guess it is doing more aggressive vectorization, but to be checked. I see Adrien is typing something. I will wait for a question, if it is. Oh, it's a question for the real expert, but the compiler generates better than us when trying to compile. What do you think? I would say yes, but depends on the complexity of the use case. I will ask for a comment from Adrian with an H. Adrian, a question for you. We have another Adrian, which is asking, is basically the compiler, is it better than us when trying to optimize? What do you think?
Depends what kind of optimization job you're trying to do. I wouldn't want to do stuff like register allocation myself. I don't trust compilers on higher level things like data layout or parallelism.
If you have a complex, normal use case, I would say, you know many things that the compiler does not know. So you may be more efficient for what concerns moving data, etc., because you know what you have in mind. So it depends. The answer is it depends. Okay, I think it's time to stop here. So later question on the SYCL channel, please. And we meet again this afternoon with Fortran, I think, at 2 o'clock. No? Oh, sorry. And there's something before. There's a presentation of some of the computing center in Netherlands. Which time? 1:30. Okay, so we are back at 1:30. Thanks, everyone.